I'm Michael Hope. I'm a postdoc at EPFL in Switzerland, working in the Laboratory of Magnetic Resonance with Professor Lyndon Emsley. So I'm primarily working on hybrid perovskites, which are solar cell materials. Exciting because they have the potential to be a lot cheaper than conventional solar cell materials. But at the moment, there's still some challenges in terms of improving the stability and the performance. And so I use NMR to study the atomic scale structure of these hybrid perovskites to try and work out how to improve the efficiency and how to improve the stability. For us, looking at materials, so solid state NMR of materials, it's the atomic scale structure that we get from NMR that makes the real difference. So the conventional way of looking at materials is with diffraction-based techniques. It's very useful. It gives you the bulk, long-range structure of crystalline materials. We use NMR, for instance, in the hybrid perovskites, is to look at dopants, so low concentrations of dopants, where it's really the environment around that dopant that we want to look at, or we're looking at amorphous materials, or we're looking at thin surface coating. So for instance, we can prove that a surface coating has gone on top of a perovskite solar cell material. And this is information that's very difficult to get from diffraction techniques, where you're only looking at the bulk structure. Saying before, one of the main drawbacks, the main drawback of perovskite for solar cells is that they degrade under environmental conditions, in particular on exposure to light. So clearly that's a very big problem for a solar cell. We're really trying to understand why these materials degrade when they're exposed to light and how we can prevent that. So this means trying to study the degradation mechanisms when you expose these materials to light. So it's addressing the climate challenges, moving away from fossil fuels and using green, renewable solar energy, which is the most abundant resource we have on the planet. We just need to work out a way of harnessing that. And really why we're focusing on perovskites is just a question of cost. The cheaper we can make solar energy, the faster it's going to be adopted. In our lab, one of our main focuses is on dynamic nuclear polarization. So this is a technique to enhance sensitivity of NMR being an inherently insensitive technique. And so this has been very successful, but actually quite difficult to apply to perovskite materials for a variety of reasons. But recently we were able to overcome these challenges and actually get to the point we could look at the surface coating on a single thin film. Thin film is maybe a micron thick, but the surface coating on top, it's only tens of nanometers thick. It's extremely, extremely mass limited, but now using dynamic nuclear polarization, we can look at these surface coatings on device relevant thin films. That's what we're very excited about, and now taking this further and looking at how these films are affected under environmental conditions, etc. So I think really an enabling technology to take this research further. Building on these previous results, now we can look at these thin films. We want to extend this and look at degradation, playing around with different conditions, and then different perovskite compositions and treatments and additives. And so there's now quite a wide space that we've opened up that we can explore in. So that's what the direction we're excited about going in.